All right. People are starting to come in, so I will get us started. Welcome everyone to our first of two special webinars for celebrating the 50th anniversary of the Institute of Acoustics. Today we have Dan with us, which we are very excited about his historical talk. It's going to be really great. Also join us next week. We have another talk on the 12th, and these two will be our series for the 50th anniversary. Just as a reminder, registration for the hackathon that we're going to be running is closing this coming weekend. So if you want to join, there are still a few spots available. And please do register. All the information can be found on our website. And yeah, again, that will close on Sunday. So let's go ahead and get started. Today we will be talking with Dan Sternlicht, and I'm very excited to hear his talk. So I will hand it over to you now, Dan, if you're ready.
Great. And I guess we will do the sharing here, right? So let's see. Okay. Can you see the slides?
Yep.
Okay.
Okay. Hey, pleasure to be here. I want to say thank you to Alan Hunter and to Maddie Ficino for giving me the opportunity to address this forum. This work is going into a course on Navy sonar design and analysis that is being developed by the Naval Sea Systems Command Laboratories at Newport, Rhode Island, and Panama City, Florida, where the emphasis is on mine countermeasure and anti-submarine warfare (ASW) sonars, and where part of the philosophy is to look back while looking forward, really to discipline our workforce in recognizing leap ahead innovation. So I thought I would start this off with a slide on the evolution of sidescan and multi-beam sonars. I presented this at an ASA conference 7 years ago that Alan also presented in. And I think it had some influence on leading to an invitation to this talk. This is the story I knew when I was doing my graduate studies in the 1980s and 1990s. You know, that is in the 1960s, you had Doc Edgerton of MIT and Marty Klein experimenting with turning a sub-bottom profiler, on the side and getting a very, primitive side scan record of the seafloor. And their companies would eventually form Edge Tech and Klein Associates. And locally for you, I have seen some sonographs by the National Oceanographic Center from the early 1960s. And that was technology that would lead to the Glorious system. And then we have similar timelines for the development of multi-beam echo sounders on the bottom of the graph. It wasn't until I started working for the U.S. Navy that I became aware of the CMark 1 or shadowgraph side scan sonar, which I believe is now, more or less acknowledged as the first of these types of systems, with designs, dating back to the early 1950s. This is not to be confused with the CMark seabed mapping and remote characterization system developed by the University of Hawaii in the 80s, which coincidentally enough was the first system that I personally worked on. The shadowgraph was conceived by Panama City's Julius Hagemann and would give rise to many of the mine hunting sonars that today are part of the U.S. and NATO triad of airborne, surface, and DoD mine countermeasures. Here you have towed U.S. systems evolving on the top, systems for UUVs evolving through Panama City, and others in the middle, and the technology being exported to France for development by companies like Thales. All these variants now, of course, operating as high-resolution long-range synthetic aperture sonars. Hagemann is now considered by many as the father of naval mine hunting. And I'll have, a little bit more to say about him in later slides. A little anecdote, some time ago, I gave this lecture at a veterans society, this lecture on the sidescan sonar, at a veterans society in Syracuse, New York, where I was continuously heckled by a 93-year-old veteran who in his career had been a program manager at the local General Electric, which is now Lockheed Martin. He kept saying, something to the effect of, well, we made the pioneering and the best, mine hunting sonar. And, after sitting down and talking with him, I realized he had a point, mainly that I wasn't telling the full story. So one motivation in developing this course is to tell the full story in both mine countermeasures and in ASW. And the story is nothing less than fascinating. With big personalities and leap ahead innovations that so characterize our creed and really our trade. So why do we care? The left side, I got to start this up here. Yeah, the left side of this slide shows the modeling of the bubble that is caused by a mine detonation. And this is a model that was created by the NAVC laboratory in Indian Head. Now, much of the damage comes from the shock wave, which can rip a hole in the hull and shake and damage machinery really throughout the ship, often causing significant casualties. I'll play this again. So this bubble can actually lift the ship out of the water, practically breaking it on its spine. So, it's very important to carefully carry out shock tests on these new platforms. So I'm going to show you NSWC Carter Rock, another NAVC lab, carries out these shock tests and plans for them. And I'm going to show you the shock test for the Gerald R. Ford over on the right.
4, 3, 2, 1, go!
So I think that'll do. I think you get the point. This is a slide I typically use not only to awaken my audience, but also to introduce the importance of mine countermeasures and platform design too, of course. So I'm going to be talking a lot about U.S. systems here, so I thought I'd kind of throw up the code, so to speak. These are you're going to see a lot of these through this talk. You have your own in the UK, and you'll see a lot of those too, actually. These are the Army Navy equipment designations, or AN. And typically the three letters associated with a system. The first is by installation, and second is equipment type, and the third is function. So installation, A for airborne, S for shipboard, P for portable, U for multi-purpose. Second letter being the equipment type. The ones we'll be mostly concerned with are Q for sonar and N for navigation. And the third letter denotes really function, S for search and detection. Q is kind of a catch-all for a special purpose. And you might even see a B in there somewhere. B, as far as the installation goes, is for submarines. So we have a couple examples, the AQS-14, airborne, towed, sonar, search and detection, shipboard is SQQ, handheld, PQS, etc. You kind of get the point. So, so the two major precepts of mine countermeasures are to hunt when you can and sweep when you must. Through most of recent history, we have had to sweep, cutting cables, tricking the mines into exploding. Hunting is locating and identifying the target, typically destroying, disabling, or marking them to be avoided. You know, that was pretty much unachievable in any scale until the advent of mine detection sonar. You know, which I have actually categorized into three generations shown bottom left, and where I've set the kind of the rough divide between the old and the new at the 1991 Gulf War. So, you know, this chart in the center shows the Iraqi minefields and the associated Desert Storm operations of February 1991. There were over 1,000 mines laid in those boxes and mine lines. And it took a considerable effort to clear that lane in the center from right to left, which on the screen actually looks like a white strip of correction tape. You can see the approach out of the east, and then a box just wide enough for a battleship to maneuver and provide naval gunfire support for the U.S. Marines and Arab coalition forces that were moving up the coastline. These minefields made the prospects of an amphibious assault potentially costly, and actually resulted in 2 mine strikes on U.S. warships, which you can actually see marked above and below the clearance lane. This is a classic example of what we call asymmetric warfare, where $1,000 devices keep billion-dollar platforms at bay. And in that conflict, the U.S. brought a mix of wares. The SQQ-32 on the new MCM Avenger class ships. You can see some pictures in the bottom right. Along with our workhorse ocean class minesweepers that had been around for decades, and they were fitted with the SQQ-14 and our helicopter towed side scans, the AQS-14. The United Kingdom brought their Hunt class MCM vessels with the Type 193M ASDEC, a fine sonar, similar in principle to our shipboard systems. And you can see a picture of the dual operator station for this system at the bottom. By the way, it's very difficult to find photos of these old British systems. So if anyone out there has them, I'd love to get a hold of them. Incidentally, the British Hunts were actually the star performers during Desert Storm, largely because they could maneuver around the Iraqi minefields due to the low magnetic signatures of their fiberglass hulls. It would take the work of 11 nations about a year to clear out the rest of this material. So from a historical perspective, I've broken down the MCM sonars into 5 categories spanning 3 generations. So in the early days, sonars and their electronics were bulky units requiring much power. So the first generations really saw the emergence of mostly shipboard systems. This would be from World War II to the early 1960s. In the second generation, from roughly the mid-60s to the Gulf War, we see the addition of towed and diver-held sonars. And then the third generation really represents modern day, where you have an emphasis on unmanned technologies, but also, and perhaps a bit of a thematic anachronism, the use of dolphins for mine hunting. Perhaps best referred to as a prehistoric system. And we have similar timelines, for submarine and surface ship ASW sonars. Again, full disclosure, my focus has been on U.S. systems, but I try as much as possible to tie this in to what was happening abroad. And I hope to learn more from discussion here, as well as from any follow-up conversations. So the evolution of the 5 categories are shown here, and really each one could be a full lecture in itself. Today, I am of course going to touch on the evolution of the sidescan sonars, as we already have a bit, and specifically their airborne application that is being towed by helicopter. With the possible exception of dolphins, more people are aware of the side scan these days, primarily because of the role in mapping large tracts of the ocean floor and discovering, many famous shipwrecks. But we're also going to talk a bit about the shipboard minesweeper systems, which really don't get very much press. I'm also going to dwell a little bit on what's considered in the U.S. the first successful battle-tested mine detection sonar. That's the guy in the kind of the bottom left in kind of bold and in yellow. It's called the QLA or Hell's Bells, which would have as its legacy the series of actually diver-held devices you see throughout the bottom of the chart. But first, let's go back to the beginning, with the foundational period of sonar before World War II. There are a lot of great stories here, many involving what the Acoustical Society of America refers to as the pioneers of underwater acoustics. So that's those 5 distinguished-looking gentlemen on the top left of the graph on that medal. So at the turn of the 20th centuries, signal bells started to be used as navigational aids. They were on light ships and buoys connected to ground stations, and ships operating in the fog, would have waterproof microphones. The word hydrophone hadn't been invented yet, and these were connected to telephone receivers up in the bridge. These technologies were rolled out by a very innovative organization known as the Submarine Signal Company, which was involved in many of the sonar advances of those early years and would eventually become part of the Raytheon Company. In the 1910s, Reginald Fessenden, that gentleman on the bottom left of that medal, would be hired at the company by Harold Fay, the gentleman in the middle. Fessenden was a brilliant engineer, developing probably the first underwater acoustic transducer, which could take the place of the bell, but also eventually used for echolocation, photometry, and submarine communication. Fay, no technical slouch himself, had the business acumen. Though the two of them were often, I don't know how to explain it, furious at each other. There's a lot of interesting personal dynamics. One was a purist, the other was a realist. But they, along with Langevin across the pond in France, and the gentleman actually pictured in the bottom right of the medal, those three, would really usher in the era of active sonar. Langevin is reported to be the first to even echolocate off a mine. So, some call him the father of mine detection sonar. We certainly have no lack of matriarchs and patriarchs in this field. So in the 1930s, you had the advent of so-called searchlight sonars, and that's shown in the top middle of the diagram. This was hull mounted and steered at first physically, but eventually electronically. You'd steer it toward a suspected target. It could be used in active or passive mode, with an operator listening for the sounds of machinery, or from the echo of an active ping. And actually, the UK were the leaders in this area. And in the early years of World War II, the UK shared, your advances with us in the US as part of the Lend-Lease Act. And we learned at an accelerated rate, eventually developing scanning sonars that automatically produced the views of these planned position indicator displays, which you see on the right, which really gave the operators a bird's eye view of the underwater scene relative to your own ship in the middle. And these PPI displays are still used on many UK and US and really worldwide minesweepers to this day. During the war, these types of sonars were used primarily for anti-submarine warfare, but detecting something the size of a mine was very challenging. So that brings us to the QLA. This pro-submarine system, I mean, that's what they called them back in that day, anti-submarine warfare, pro-submarine warfare. This system was an early FM, frequency modulated sonar, but not of the pulse nature, which is part of most modern echolocation systems. Rather, this one was continuous in time, a CTFM system. They didn't have the pulse compression capabilities that we have today. It would repeat this reverse sawtooth FM waveform that you see in the center, starting at high frequency and dropping down to low frequency. Typically, you would be receiving an echo from a target at a higher frequency than you were currently transmitting. And by simply heterodyning the two, you get an indication of range. And each range frequency band represented a geographical ring around the polar display on the bottom right. And of course, these bands were filtered out by discrete component electrical circuits, made up of inductors, capacitors, and resistors, operations we do in code today. And you can see the detected objects in front of you, where these, of course, would be mines suspended in the water column, tethered to the seafloor. Detecting bottom mines was pretty much out of the question during World War II. So a major reason the sailors liked the QLA was for its audio, which its audio went along with the display. First of all, a high-pitched sound meant the target was far away, and that pitch would get lower and lower as you approach the target. Second, they could tell the character of the target through the audio, which, if a mine was reportedly a very haunting sound, hence the name Hell's Bells. So in the summer of 1945, 9 U.S. submarines used the QLA to break through the minefields of the Tsushima Strait. This is the strait separating Japan from Korea, you kind of see in the bottom middle. And they basically wreaked havoc on warships and commerce in the Sea of Japan in what was called Operation Barney. Some of the subs from that operation came so close to the mines that they actually rubbed up against the mine tethers. And it was said that some of the operators would have nightmares around the sound of that sonar system. Though it was so successful for the submarine fleet, the QLA wasn't actually chosen for minesweeper use after the war, but it did transition to Navy diver-held sonars, and that basic CTFM design is still used to this day, which I think is pretty cool. Now the QLA, is considered by the U.S. To be the first successful, mine detection sonar, at least one, used in combat. But you can often find little caveats to these kinds of statements. For example, just last week, I pulled this quote out of a mid-war U.S. Navy mine disposal handbook, stating that the first use of sonar to avoid mines was really a British exploit during the 1930s Spanish Civil War. I haven't found any other references to this, but I did find a reference that British losses to mines while serving on blockade duty inspired the development of a mine detection adjunct for the Type 129 ASW sonar, which I actually listed earlier in that larger diagram. So, just like in the US, there was a lot of experimentation going on. So I'd like to draw attention to the blue box under the year 1950 in this diagram, which lists Hageman's review of mine location devices. Here, Panama City's Julius Hageman led a panel of Navy scientists and officers, which reviewed and evaluated all the innovations that came out of World War II. And you can imagine, Hageman was actually a German scientist during World War II, so he really had the full visibility. And they used this to chart the future course for our minesweeper sonars. And they basically greenlighted the transition of General Electric's, GE's underwater object locator into what would become our minesweeper's UQS-1 hull-mounted mine detection sonar. And I would operated through the 1950s, perhaps similar in configuration to your Type 2193 today. We would in the U.S. lose a number of ships to mines during the 1950s Korean War, which actually led to accelerated transition of these systems. So, with the addition of a high frequency mine classification aperture, and this being inspired by the UK Thomson Marconi Type 193, this would be upgraded in the 1960s to the aforementioned SQQ-14, a very capable system. This had a low frequency, a long range scanning PPI display for detecting targets at ranges really exceeding 1 kilometer. And then a separate band, steerable, independently steerable, that's basically forward look aperture, for classifying those detections. Each sonar having its own operator and its own console, as you see in these photos, and actually in the earlier photo of the Type 193 combat station that I showed in the Gulf War slide. Incidentally, these two General Electric systems were the objects of pride for my 93-year-old heckler in Syracuse, New York. And amazingly enough, I have even found his name on some old classified documents dating back to the 1950s. It's pretty amazing to come across them. So the 14 would be replaced by what we call the squeaky 32, the SQQ-32, which has a lot of UK and French influence. It'd be fitted to our MCM ships, and it made its debut in the 1991 Gulf War, and it is still in service today. And its counterpart here, where you are, is the Type 2093 made by Thales, which of course acquired Thomson Marconi some years back. So on the upward tack of that box, in the center, Hageman's report really expressed the need for a sonar that would produce a picture quality image of the seafloor. And that actually led to his invention of the shadowgraph. One could say that the first side scan sonar was invented by a German scientist working in Panama City under the influence of recent British and Canadian ASW sonar designs. So in 1947, Hagemann leaves war-torn Germany and emigrates to the US along with Werner von Braun, right, the famous rocket scientist, and really 1,000 other scientists under Operation Paperclip. And at the Panama City Laboratory, he comes up with the idea of mounting a sonar on the side to create a composite image of the seabed. Mine detection sonars of the day being mostly forward look or the sector scan varieties that we talked about. But we all stand on the shoulders of those who came before us in this field. And he got his idea from the UK Type 162 ASW sonar, which was side mounted in the hull of a ship and hull of a destroyer, and looked for the silhouettes of bottomed U-boats. The one remaining artifact of this ASW side array are really the hull openings on the World War II era Canadian destroyer Haida, now a museum ship shown on bottom left, and you can actually see the marks where the sonar was actually mounted. So the first shadowgraphs were built by Westinghouse, now Northrop Grumman, and installed on the USS Venture Ocean-class minesweeper in 1960. You can see a photograph of that on the bottom. And these really saw service through the early 1990s. And check out this imagery on the bottom right. I know it's not a very big picture, but I think you can kind of get the idea. That imagery is really quite fantastic. Considering these graphs were made in 1950. You have a rocky area, sandy area, an area with targets. The reason is this was a 1.5 megahertz system. Okay, and the side scans that were built in the 60s after this were really of the kilohertz variety, much coarser resolution. Of course, being at such a high frequency, you only had swaths of about 60 meters, about 30 meters per side. But I would think the modern equivalent of that would be a marine sonic sonar, if people are familiar with those. But imagine the excitement, right, of imaging large tracts of seafloor for the first time. Boy, I would have loved to have been on that team. So the shadowgraph's successor, okay, was the AQS, what we call the AQS 14, which reached initial operating capability in 1984. This is just a little story here. In July of 1984, which is just a little more than 40 years ago, merchant ships transiting through the Gulf of Suez and the Red Sea came under attack. Sounds familiar, doesn't it? 20 ships from July through August were struck by mines, and it would take coalition forces from half a dozen nations to sweep and to hunt the area, rendering it safe. And new to the field just that year was the AQS-14 mine hunting side scan, towed by our MH-14 Airborne Squadron, and of course supported by NSWC Panama City. We were called the Naval Coastal Systems Center back then. 40 years later today, Red Sea shipping is again under attack, this time primarily by missiles and drones. And the U.S. Navy is taking a lead role in keeping these sea lanes open along with our allies, and continuing its tradition. The NAVSEA Warfare Center has actually stepped in to upgrade our ship combat systems to counter many of these new threats. So just some things never seem to change, right? 40 years later. So to close out this section, to reiterate, Julius Hagemann developed the concept of the mine hunting sonar, but he also provided guidance for transition of our early minesweeper sonar systems. So that status as a patriarch in naval mine hunting is probably well deserved. And how am I doing on time, Maddie? I don't have the clock up here.
You're at 2:36. You still have plenty of time.
2:36?
Yeah.
Okay, that's no, your time. Okay, right.
Oh,
Okay.
right.
We're getting there. Didn't think I'd been talking for 8 hours. Okay, so these are the current and emerging MCM systems. So, I put some of the ships on the top. I mentioned the MCM, the Avenger class ship, and in the front of this ship, actually, in front of the forecastle, you can see a winch there. That's part of the sonar chest, and this variable depth sonar that you kind of see below it, the squeaky 32 would be lowered down from that area, and they'd lower it down below the thermocline, right, to make sure you can get mines in all water depths. And of course, these ships actually had the neutralization capability too. So this was a direct detect to engage capability, which most mine hunting ships have. And these are being phased out and replaced by the littoral combat ships. You see the two varieties there. And these are more interoperable. They have what we call a mine warfare mission package, which has a variety of sensors and gear. And then you have the UK Sandown class systems, and of course with your 2083 and 2093 and 2193 sonar systems. I've shown the HMS Penzance there because I'm a closeted Gilbert and Sullivan fan, so I had to put that ship up. But you see the U.S. Kind of acoustic systems on the bottom, the 32. We have the two-towed side scans, the 20 and 24, the Mark 18 UUV systems on the bottom, Knifefish system, which is more of a non-imaging system, and then of course our Mark 7 dolphin and diver teams. And really most of these newer sonar systems are of course synthetic aperture capable now. All right, so getting into the modern age here. So the biggest thing to hit mine hunting in this century is the naval transition of synthetic aperture sonar. This is work that both Alan and I have played a hand in. Alan coming from the University of Canterbury, where much pioneering work was done in this field. The synthetic aperture technique, whether in sonar or radar, combines multiple transmissions coherently along the path of the sensor, along the path of the sensor trajectory to construct a long virtual or synthetic array of receivers. In the more simple single transmission side scan process, the along track or resolution or azimuthal resolution of the area imaged is indicated by the projection of the sensor's beam pattern onto the terrain, as shown in that larger blue balloon. However, with the creation of a synthetic array, which can be made for much longer ranges, the along track, azimuthal resolution can actually be made quite fine and even constant in range, as shown by that very narrow strip. Inch spatial resolutions are not uncommon. So in sonar, when these techniques are applied at sufficiently low frequencies, where sound absorption in the ocean is reduced, a modest-sized sonar, like one you can fit on a small UUV, can generate an image with fine, constant azimuth resolution comparable to that of high-frequency systems, like the shadow graph, right, that I showed earlier, but with a much longer range potential. So, I have a full lecture on the origins of SAS, perhaps for a future talk. However, just briefly, this slide shows a timeline of synthetic aperture sonar and their influential technologies. Developments in SAS are shown in blue, while those in some of the foundational technologies are shown in black. I also show other influential technologies like radar, down near the bottom, primarily SAR, but also recognizing contributions in medical acoustics, geophysics, materials, and computer science. And in black, starting from the left, you can see the developmental trajectory of the seabed mapping sonars that we've discussed. And the way to read the SAS part of the timeline is really down the diagonals, commencing with early patents and reports, followed by techniques to enhance range, detailed studies of the medium, really all the way down to resolution and to really high resolution bathymetry at the close of the millennium. Then starting again at the top, we have the implementation of unmanned undersea vehicles and rolling down to some of the current trends. So of course we should have a few examples of this revolutionary technology. Here we have fine resolution, high frequency imagery created with the Office of Naval Research's dual band small synthetic aperture mine hunter, or SSAM system. You see an old cargo ship with lobster traps. This was taken in the Chesapeake Bay. And imagery of a cement anchor block, the block and the cable and a sunken buoy, where you can actually see the weight of the anchor block embossed on the surface. That's that 1,800. It says 1,800 kilograms, which is about the size of a 1 meter cubed block. So using the vertical aperture of the array, we can also calculate depth values in the scene, allowing us to render this into 3 dimensions, as you can see on the bottom. So we have imagery and bathymetry using the high band. Next, we pull in the mid-frequency band on the same platform, where a high band image shows this detailed seascape that's over on the side. I'm going to try using my cursor here. I'm assuming you can see that. You see there's a pothole there. And the corresponding mid-frequency image, taken at the same time, using longer wavelengths, actually penetrates into the sediment to image this sub-bottom, like lattice-like geology. But there's that same pothole, right? So this really is the same area. And the bottom pair actually shows detailed images of objects on the seabed in the high band on the right side, and about twice as many in the low band on the left side, and that's because many of these are buried. And we can actually go even lower in frequency using a very low frequency synthetic aperture sonar called the BOSS, the Buried Object Scanning Sonar, which makes these buried objects even more clear. And while the resolution isn't as fine, at this very low frequency, you can match these sensors with like magnetics to better inform your decision as to what's going on down there. So different spectral views of the world with some very powerful tools. So getting close to the end here. So these are current and emerging trends. Certainly in our Navy and navies around the world, the emphasis is on gear that's faster, unmanned, and platform interoperable. And this includes advances in materials, mechanisms of transduction, faster processing hardware, low size, weight, and power and cost, what we call SWaP-C, but also noise reduction, trying to get extended ranges, greater area coverage rates, three-dimensional bathymetric and tomographic imaging techniques, which you see some on the right there. And then, of course, the ability to peer into the sediment to resolve buried threats. Automation, right? Huge. This includes automatic target recognition, seabed change detection, through the sensor environmental characterization, and, of course, the ability to conduct independent autonomous operations. And then some of the questions we are asking as we assemble this course are, how do we expect advanced materials and quantum technologies to affect future sonar design? Another, can ATR be improved, right, by blending physics-based approaches with recent advances in pattern matching? And more broadly, what is the future of sonar system design and analysis? And that is, very much the theme of this course and textbook, which will teach acoustics, naval sonar design and analysis, and a little bit of history, where we will study, quantitatively how historical systems performed in their key military engagements. So I just want to end by saying that that one of the kind of fun parts of this process are finding the artifacts. I recently visited Battleship Cove in Massachusetts, where these, you can see these warships here, and snapped a few photographs of the submarine, a USS Lionfish's sonar console, which you can see on the left. And on the right, yes, that's Clark Gable, right, standing nearby nearby the sonar operator, actually, from the 1950s movie Run Silent, Run Deep. And these are these little gems of films out there, which show historical sonars and their operators. There's your famous old film, The Cruel Sea, and more recently, The Hunt for Red October, and the movie Greyhound with Tom Hanks. And of course, the characters are all ASW sonar operators, and I'm hoping we can do our part to raise awareness of the MCM, mine countermeasures sonar operators, and maybe they'll become characters in movies someday too. Well, that's the end of the formal presentation. I want to thank you for your attention, and I'm happy to take any questions.